Hey guys, today we're going to be talking about section 1.2, properties of real numbers. I already have the first page filled out mostly, so if you need to pause it and to catch up as I go along, do so. Alright, let's get started. Circle the pair of numbers that are opposites. So opposites mean the positive and negative version of the same number. So 7 and 1/7 are reciprocals, if you remember that from Algebra 1, but they are not opposites. But -4 and +4 are. Nope. 5 and -5, yep, those are opposites. And 4 and absolute value of 4 are both +4, so they're not. The next one says write the opposite of each number. So if you remember, absolute value kind of makes it positive. It's how far away is that number from 0. So this is actually +3. So the opposite of +3 would then be -3. Then 1 is -1. -17, make it +17. 1/2 becomes -1/2 for its opposite. Square root of 16 is 4. Opposite of that, -4. 0 isn't really positive or negative, so you can just put 0 again. I guess it doesn't technically have an opposite, I wouldn't say. So classifying numbers, we have real numbers, which is the set of all, the set of all real numbers includes all rational and irrational number. Pretty much any number that is not imaginary, and we will talk about imaginary numbers later. So everything in this box, negative numbers, positive numbers, you got fractions, um, you got square roots of numbers, you even got 0 included. These are all real numbers. All of these are also included in real numbers. So if you broke real numbers down into mini sets, you could have natural numbers, whole numbers, integers, rational, and irrational. These are all sort of little subsets of the real numbers. So let's take a look at circle all these real numbers. So pretty much everything in here is real except this one. If you took the square root of -1 and plugged it in your calculator, it would give you an error in your calculator. And that is because this is not a real number. It is imaginary. And if that scares you, it shouldn't. We will cover this in a chapter, just not this chapter. Next, for number 4, circle the real numbers that are also integers. So integers are pretty much positive and negative numbers, along with 0, that do not have decimals. So -3 is good. Square root of 5, if you plug it in a calculator, that is a really long decimal that does not repeat. Again, this isn't even a real number. Square root of -1. 0 is fine. 7/8, that's not a integer because, again, it's a decimal if you plug that in a calculator. So how does the set of real numbers differ from the set of integers? Well, the set of integers includes rational and irrational. Again, so rational can be decimals. Irrational are things like square root of 5, which are decimals that go on forever but don't repeat. So the set of real numbers is bigger than the set of integers because every integer is a real number, but not every real number is an integer. That kind of thing. All right, let's take a look at the next sheet. So here we go. Classifying a variable. So your school is sponsoring a charity race. If each participant makes a donation D of $15.50 to a local charity, which subset of real numbers best describes the amount of money raised? So I'm going to run off to the side here, just in case if you don't remember from Algebra 1. So you've got real numbers. Oh, sorry, I'm going to start small and work my way out. So the very smallest one is called natural numbers. I'm just going to put an N for natural. So natural numbers are things that came natural to us. If you look and start counting things, you can start counting from, you see 1, 2, 3, 4. So you got 1, 2, 3, yada yada yada. That kind of came natural to us to count like that. So you have natural. Now one step further is you also have whole numbers. And the only thing different from a natural number to a whole number is now you include the number 0. 1, 2, 3. So 0 is now included. So this kind of came natural to us. The number 0 did not come natural to us. It was sort of debated on. It was actually quote unquote discovered, and people debated on if 0 was actually a real number or not for quite a while, until all the mathematicians back in the day said, yeah, we'll include 0, and now we've sort of expanded on our natural numbers to be whole numbers. So I'm going to make a bigger circle here. So natural is the smallest, whole numbers include 0. The next we have is integers. So everything that we've already had so far, so then 0, 1, 2, 3, blah, blah, dot, dot, dot. Also their opposites. -1, -2, -3, dot, dot, dot. These are all integers. Okay, so if you imagine every natural number is included in the whole numbers. Every natural and whole number is also included in the integers. So we're sort of getting bigger and bigger as we go out. So after integer, we have the rational numbers. Rational. So all of this stuff, now we're also including fractions. Every integer, and they're in betweens. So what's in between 1 and 2? Well, 1.5, 1.6, 1.7, all of that. But technically, it still has to be represented by a fraction. So if you can write it as a fraction, then that is a rational number. So you still have numbers like 0, 1, 2, -1, -2, but now we also have -1/2, +1/2. We have -7/8, +7/8, all of that. Anything that can be represented by a fraction and a decimal. So that is all the rationals. And then one step further, so this is rational. I really should have, rational and real both start with an R, so I'm just going to write out the word real here. So real, sorry, I'm getting ahead of myself. So you've kind of got, these are all right here. The irrational numbers are kind of like on their own separate sort of bubble. So you have irrational numbers. I'm just going to do IR for irrational. So irrational numbers are numbers that can't be represented by a fraction. So you've got things like the square root of 2, the square root of 3, things like that. You also got that famous math symbol that's used for circles, which is pi. You might have seen that in geometry. So pi is irrational. It's a 3.14, yada, 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 yada. It keeps going on and on forever. These are like non-repeating decimals, and you really can't represent pi or radical square root of 3, square root of 2 with a fraction like 7/8 that includes the whole thing, And no, making a fraction over 1 doesn't count. So you have irrational numbers such as this. Okay. Now when you include both of them and you say, all right, this whole thing here, everything, all of these guys here, these are all real numbers. These are all real numbers. Okay? So reals include rational, irrational. That's usually what we say because that all of these numbers are also rational. So there you have it. Okay. So looking at this. Again, donating $15.50 to local charity, each participant. Which subset of real numbers best describes the amount of money raised? Okay. Well, let's see here. Well, technically, if nobody shows up, circle the values below that could represent the number of participants making a donation. Oh, so if people are showing up to make a donation, it doesn't make sense to have like decimals, fractions, or irrational numbers. So 0 people could show up to make a donation, or 10, or 150. You can't really have half a person. All right? So now, which one of these sets of numbers best describes the amount of money that we would make? Sorry, we're still actually talking about the number of people showing up. This is about number of people, sorry. We don't really care about the money. We're talking about the number of people showing up to make a donation. So, we have 0 included, we have 10, we have 150. So no fractions, no negatives. So what's the smallest subset we can have? Well, natural is close, but because we have 0, we have to step up one further and go with the W whole numbers here. So the answer would be whole numbers. Okay. Now, it wouldn't be wrong to say real numbers, but real covers everything, right? So to be the most specific answer, we would say whole numbers. It's the smallest one that still fits with the options we have. Okay. All right, number 2, graphing numbers on a number line. So let's see here. Find the integers each number is between. Use a calculator round to one decimal place. So if you've got a calculator, great. I'm going to be telling you some of these answers here. You do square root of 3 in a calculator, it tells you 1.7. And that makes sense because the square root of 3 is between 2 and 1. Square root of 3 is between the square root of 1 and the square root of 4. So if you remember that the square root of 1 is 1, the square root of 4 is 2, it makes sense that the square root of 3 is between 1 and 2, and it's 1.7. So that kind of makes sense if you're thinking number line. So think of the fraction form, negative 1.4 repeating, which is about 1.4, which is about negative 1 and 4 tenths. You know, if we really want to make a fraction form, probably not going to do this too often. So negative 1.4 repeating is between negative 1 and negative 2. So let's think here for about 1/3. 1/3 is got to be between 0 and 1. So let's see here. How can you estimate square root of 3 without using a calculator? Well, kind of like the same thing we just talked about right here. Because the square root of 1 is less than the square root of 3, which is less than the square root of 4, then 1 is less than the square root of 3, which is less than 2. So let's graph the number line what we have here. So negative 1 is right here. So negative 1.4 repeating would be, you know, in between negative 1 and 2, so a little bit over here. That's the negative 1.4 repeating. Again, negative 1.4 is more negative than negative 1, so it keeps going left. A lot of people put that right here, which is wrong. Let's see what we have next. We'll have positive 1/3, again, between 0 and 1. You are 1/3 of the way to 1. Okay? And then the square root of 3, which we already says between 1 and 2. But because it's 1.7, I'm going to put a little bit closer to 2. Then I'm going to put it to 1. There you have it. All right, scrolling down. Ordering in real numbers. How do square root of 26 and 6.25 compare? Well, find the perfect squares close to 26. So we know that 5 squared is equal to 25. All right. We can also find a square root that is, find a square root that is a perfect square close to 6.25. So square root of a number close to that. Well, I know the square root of 36 is 6. You'll see what we're doing in a second here. So, where's my next sheet at? Here it is. So what are we doing? Well, yeah, we're kind of using like mental math here. This is using mental math instead of just plugging this in a calculator. It is nice to know how to do this with mental math. So, because the square root of 25 is less than the square root of 36, all right, and both of these are obviously less than 6.6 or 6.25. So now write the greater than or less than to compare the square root of 26 and 6.25. I don't know why I can't say it. So the square root of 26 is less than the square root of 36. So obviously the square root of 26 has to be less than 6.25. Okay. If this is 6, then this is way less than 6. And obviously both of these are less than 6.25. That's kind of like the mental math they want you to do. Obviously, you could have plugged this into a calculator and immediately saw it was less than 6.25, but that kind of defeated the whole problem. Okay, here we go. Uh, Properties of real numbers. So, I know I'm with you guys, especially if you're a student that hates memorizing things. I remember having to do all the flashcards for anatomy and learn all those bones, all the muscles, the tissues. I know it could be a lot. Um, this is one of the few times where, unfortunately, you do just kind of have to memorize the name. Most times, as long as you know how math works and you understand how the relationship between numbers, you usually don't have to memorize names. But in this case, you do. So we do have these names for properties, and I'm going to tell you my way of remembering them. So we have closure property, which just says if you add a plus b is a real number, or you can multiply them. So we have two routes. We have an addition route and a multiplication route, just to show that it doesn't matter if you're adding or multiplying them. All these properties still work for both. That's why we have like two separate columns here. So if you add two things together or you multiply two things together, you get a real answer. And I just kind of think case closed, right? Case closed. 5 is a real number. You add it to 7, which is a real number. That equals 12, which is a real number. Case closed. It just when you add two real numbers together, you also get a real number, and that's it. Case closed. So that's the closure property. So here's where it gets a little tricky with commutative and associative. Commutative. If you do a plus b, if you do 5 plus 7, that is equal to, you flip it around, 7 plus 5. That makes sense, right? 5 plus 7 is the same thing as 7 plus 5. They're both equal to 12. That is the commutative property. Now, how do I like to remember it? I think if you are commuting to Lincoln Land Community College or something like that, you were sort of moving, right? You're hopping in your car and you're driving over there, and then you're coming back, right? So you're kind of like switching places. You're at your house, then you go to the school, or you're at the school and you go to your house. That you're commuting and you're switching your spot, okay? Same thing with multiply. So a times b is b times a. 5 times 7 is 7 times 5. So commuting means you are switching. So associative means you are not you're not moving your spot, okay? So notice how it's a plus b in parentheses plus c. That's kind of like, I don't know, 5 plus 7 in parentheses plus 3. And they're saying that's the same thing as 5 plus, in parentheses, 7 plus 3. It's saying it doesn't matter the order you add these in. If you add these first two together, then the third, or add the second and third together, then the first, they're both going to equal the same number. So I'm thinking of associative as in you can either associate these two together first or associate these two together first. You're sort of sliding. You're sliding over the parentheses. The parentheses here, and you slide them over, and they're right there. You're not moving the order. So commuting, you are moving to your community college. You're commuting to school. You're moving. Associative, you are sliding over the parenthesis. Associative has an S for slide, if you like to remember like that. All right. So it's easy to mix up these two. Commutative and associative, it's easy to mix them up. So be careful. Now, identity and inverse. Now, these two are easy to mix up. So, identity, I feel like it's kind of like you have your own identity. I am Mr. Kenny. I am my own person, and nothing you can do is gonna change that, right? So here, A is its identity, right? It's its own person, and if you add 0 to it, you do not change its identity. It stays A. If my 7 is my favorite number, and with the identity property, if you add 0 to it, it keeps its identity. It stays 7. Okay? Multiplication identity is timesing by 1. So my favorite number is 7. You multiply it by 1, it keeps its identity. It stays 7. All right, that's the identity property for addition and multiplication. Now, inverse, right? Inverse is kind of like it does change. It kind of what eliminates it. Its inverse is kind of like your evil twin brother or something like that, and it sort of eliminates you. So if my 7's my favorite number, the inverse property of addition says if you add -7 to it, if you add the opposite of it, they will cancel out and go to 0. Right? The inverse of it. Adding its opposite will make it poof and go away. Same thing, if I have 7 and I multiply it by 1/7, okay, I know it's kind of like the same thing as 7 divided by 7, or multiply by the reciprocal, but it has an inverse. It has something that if you multiply it to, it poofs and goes away. It changes and it goes to 1. Okay? So this is sort of, identity. It keeps it the same, doesn't change. Inverse means it goes to 0 or it turns into a 1. Distributive property, I feel like most people are well familiar with this. It's, if you have A outside of parentheses, B plus C, you can kind of multiply it inside to get AB plus BC, whatever those are. Okay. So I know it could be a lot, but as you practice it, you can kind of find your own little tricks and ways to remember the name. So anyway, so we have 2 outside of a parenthesis. It doesn't really matter what's inside, to be honest. I see a 2, I see a 3x plus 7 in parenthesis, and all of a sudden now I see the 2 on the other side, right? So they switched spots, okay? And there's nothing that deals with zeros and ones, right? So if you see 0 and 1s, think the identity or inverse, but I don't only see zeros and ones, so I'm thinking commutative or associative, all right? So I know it's associative or commutative, and commute, that's the one where they switch places, right? So commutative property, and we are multiplying here. So commutative property of multiplication, I'm going to match that with that. This next one, we have x, y, and 5. X, y, and 5, order does not change. You slide over this parenthesis. It's slid over. So this is that associative property, and we are just adding everything here. So associative property of addition. I see a 0. I'm thinking inverse or identity. So x plus 0, it does not change. It's x. It keeps its identity. That is the identity property of addition. Okay? Boom, I see a 1. I'm thinking inverse identity. X times 1 does not change its identity. It stays x. So that's the identity property of multiplication. Here we have an 8, and we are adding its opposite. We are adding its evil twin, and it makes it poof and go away to 0. That's its inverse. And because we're adding, that's the inverse property of addition. So up here, and I know last, it's obviously going to be this one, but you can still look at it and say, okay, we are multiplying inside the parenthesis, 5 times 2x, then 5 times 1. That's the distributive property. So, boom. All done. All right, holy cow, we're at 23 minutes. I'm going to try to speed up this last one, and this will be the last problem we do. So, identify the properties. Which property does this equation illustrate? So, it looks like we have the 3, and this g plus h plus 2, and it does 3g plus 3h. So it looks like they multiplied the 3 inside of here. So I say we have multiplication going on. These are just operations. We are also adding everything together. So we also have addition here. What's the one next? Circle the algebraic equation that models 3 plus the sum of g plus h. So that is obviously, which one of these is going to be? Oh, models. It's not going to be the same, but it's also going on. So right here, I can see this is a distributive property. So which of these also has distributive property going on? This middle one does. The equation, 3 times g minus h plus 2g equals 3g. Blah, blah. Looks like they did the same thing. They multiplied this inside. That was that distributive property. There we go. And we are done. I know there is a lesson check at the end, so if you want You can do these questions here. At the top, this little lesson check if you want extra practice. But I'm going to call it a day. And if you want, you can head over to the Math Excel and check out what's on there for 1.2. See you guys next time.